help me in welcoming Thomas to MIT Energy Night. Thomas, whenever you're ready, please take it away with your presentation.
Thank you very much for the introduction. Let me quickly share my screen. All right. Yes. So I'm really delighted to have the opportunity tonight to speak about our research project related to the quest of fusion. So we are a team working in the field of laser shockwaves, and we envision that by bringing together some pioneering techniques that we have been designing in the last years with different techniques that I will explain during this talk, we could reach sufficient pressure and temperatures where we could drive fusion a little bit like on the sun. So we are all aware about the threat for humankind about global warming. So there's no doubt that we need to find sources, carbon-free sources that could help power the energy on the planet. So the main problem there is that in fact we are addicted to fossil fuels. As you can see on this on the left chart here, there is 80% of the world's energy comes from fossil fuels. There's only a little proportion of this energy that comes from carbon-free sources. So there are alternative ways that have been investigated for a long time, and one of them being the fusion. So fusion is the energy of the stars. And governments have been funding this type of research project for many decades now, like investing hundreds of billions of dollars, because fusion could be the holy grail of clean energy, because this type of energy source is kind of limitless in terms of fuels. It has no carbon emission. So there are big projects that have been funded by governments, one of them being, for example, ITER, where the technology is based on magnetic confinement fusion, and other one, for example, like NIF, where lasers of really huge energies have been built to try to drive this type of reactions. So to be clear here, so our quest is about fusion. So there is a different, it has nothing to do with fission, of course. So fission is a nuclear reaction as well that already occurs in nuclear power plants, where the basic principle there is to break unstable uranium atoms into subproducts and this reaction will release a lot of energy. So we are all aware about the advantages of the disadvantages of this energy source. So fusion is also a nuclear reaction. So in that case, the basic principle, which has been proven already experimentally, and the most efficient way to do that is to bring together two atoms, one deuterium atom and one tritium atom. They are both isotopes of hydrogen. When there's sufficient energy to bring them together, so they will fuse, and there will be some energy outcome from that, which can be greater than the energy needed to put them together. So the good point of this fusion reaction is that it's fully controllable. There is no chain reaction, and there are almost no radioactive wastes. And because deuterium is naturally abundant in nature, it's naturally contained in water in a tiny proportion, and because there's so much water on Earth, fusion is thought as almost unlimited fuels. And there is no carbon emission, of course. The main problem of fusion is that we need to bring a lot of energy just to make this reaction possible. So we need to reach some pressure and temperature conditions, such as on a star at the center of the sun. So that's why these fusion programs were limited to government investment and the build of huge infrastructures. But I want to bring to your attention the fact that in the recent years, in the last 5 years, quite many fusion startups have emerged. In total, there are, as you can see on the left chart here, there are about 25 fusion startups. One of them being the Commonwealth Fusion System, which is a spin-off of MIT. So in total, all these fusion startups that maybe are worth like $1 to $2 billion, they came to reality because there is more and more confidence that the fusion projects are more and more a tech project than a fundamental scientific project. So there's confidence that we can find or try new technological techniques, alternatives, where fusion could become a reality, concretely an energy fusion power plant. So the vast major category of these startups are based on the magnetic confinement fusion technology. So the basic idea is to fuse this deuterium-tritium atom together by putting them in a strong magnetic field. And these startups, this technology is based on this magnetic confinement fusion from the fact that this can be downscaled to a smaller size. And that's not the case for the second category of fusion projects based on lasers. So far there have been a lot of research achievements and proofs that we can make a fusion reaction with magnetic or laser technology. About the laser technology, in fact, the first thing since the 50s has been to build huge laser infrastructures. So to date, the National Emission Facility in California is the biggest laser on the planet. So this gigantic laser that can output in total 2 megajoule is extremely big. If you look closely to this drawing, you can compare the size of a car with the size of the entire laser facility. So inside this laser facility, in fact, what's happened is that there are 100, almost 200 laser beams that are directed into a chamber. And this is a closed loop of the inside of this 10-meter big in diameter chamber. So of course, this chamber is put under vacuum. Otherwise, every one of these beams will ionize everything and we will have thunders here. So the basic idea is to put all this laser energy and to focus this laser on a target. And the target is composed of a spherical capsule. So the outer part of the capsule is metallic, and inside there is a deuterium-tritium mixture. So the laser, or the laser beams, will be focused on that target. Sometimes this target is put into a cylinder, as you can see here, but this target is just no more than 1 millimeter. So the basic idea is to use the laser to just blast this capsule. And when the laser are focused on the capsule, at the outer part of the capsule, everything will be blasted. There will be some plasma formation, and then there will be a huge compression of the capsule. And this compression and the change in volume in ultra-fast downscales will pressurize and increase the temperature of the deuterium-tritium mixture. So there have been really, really great achievements recently, like proving that we can achieve the condition for thermonuclear fusions with lasers. So there have been different trials historically since the last 50 years. First one being the direct drive, where all the beams are put together on this capsule. So indirect drive, where the capsule is put into a cylinder, and the fast ignition project, where it's a bit like a compromise between the direct drive and the use of a single laser pulse. But the major problem here, if we envision to build a fusion power plant based on laser, is that the laser takes or dumps a lot of energy. So there are only 10 to 20% of the laser energy, as you can see in this energy diagram here, that goes directly into blasting the capsule. So in terms of efficiency, there's a lot of improvement to be made here. So the efficiency in terms of how much pressure we get into the capsule and per energy of the laser lights is not so great. I mean, well, I will describe in the following our research closely related to this field, to the excitation of pressure waves with lasers. Of course, we are working with 1 billion times weaker lasers, like commercially available lasers, but we came up with some alternative technology where we kind of optimize as much as we can the pressure, the pressurization of our sample per laser energy. So I will describe the techniques that we came up we have mastered in the last 10 years. So we are specialists in the more general field of laser acoustics. In fact, we use laser to laser excite and laser detect waves, acoustic waves, sound waves in material. So the basic principle is rather simple. Like, the laser is directed into a sample, and through different processes, because there's a plethora of laser matter interaction processes, in fact, the light energy is converted into mechanical energy. So at moderate laser energy, when there is no destruction of the sample, so we excite ultrasound waves. And these ultrasound waves, they move on all directions on the sample. At higher laser energy, just starting with just a couple of millijoule laser energies. So these lasers can be used to excite shockwaves. So these ultrasound waves at higher pressures, they are called shockwaves. And we have been working in this research field for about 10 years. And we have been working on a pioneering experiment where laser shockwaves are investigated under a microscope. So we've been optimizing like how much shock pressure we can reach with a relatively moderate laser. So we came up with the idea of tailoring the laser beam, as you can see on the left here, tailoring the laser beam as a ring. So what happens on the sample surface is that the laser is focused as a ring. As you can see on the upper right video animation, so the excitation of this laser ring leads to two ring shockwave. One ring shockwave that moves away from the center and one shockwave that moves towards the center. And at the center, when the shockwave reaches the center, there's overlap of the pressure. So we call that like shock focusing. So this happens under a microscope at the micron scale. One important aspect here of this innovative alternative way of measuring shockwave is that the sample is really trivial, way more easily to manufacture than from the laser fusion projects. So in our case, the sample is just simply a water layer or liquid layer put into two substrates, flat substrates. So we have been like working on improving this shock focusing technique, and we have been able to measure the full trajectory of the shock wave until it reaches the center. And from this trajectory, we can extract how much is the shock pressure. So to give you some numbers, with a 3 millijoule laser, so 1 billion times lower than a megajoule laser, so the shock pressure is about 300,000 times the ambient pressure. So the efficiency is rather good. So still, we cannot compete with the megajoule laser, but we always are on the quest of optimizing all the laser shock excitation processes. Right now, what we are doing is that we try to reach the highest pressure as possible just by simply increasing the laser input energy. By increasing by 10 times the laser input energy, we have recently demonstrated that the pressure, the shock pressure scales linearly with the input laser energy. But still, we have anticipated that if we go higher and higher to laser energy, like 1,000 times higher, for example, we will reach a plateau. It means that the laser ring there we will lose a lot of efficiency because we will ionize everything, we will make bubbles, we will scatter the light. So the shock excitation will be less and less efficient. So we came up with a novel idea that we have recently submitted for patent, is in fact the excitation of not a single ring, but multiple laser ring. So this is somehow like an extrapolation of the single ring excitation. So we come up first with a big ring. This big ring will excite two shockwaves, one shockwave that will go to the center. And when this shockwave will cross the position of the ring number 2, we will fire the laser exactly right at this time. And then the shockwave will keep going toward the center, and then we will fire the third laser ring when the shockwave will be there. So every time the shockwave crosses a ring, it builds up in pressure. The good point is that our sample is fully optically accessible. So we can play with every one of these rings. We can optimize every one of these overlapping of this light on with these shockwaves. And these can overcome some difficulties that they have been facing for the direct drive laser excitation, because when you focus 200 beams on a sphere, the problem is that the laser intensity is not inhomogeneous at all. So the shock focus is not that great. So from this technology there, we can optimize the shock focusing, which is one important aspect there. So right now we are on the stage of understanding, improving this synchronization of multiple shock waves and overlap in one dimension. So what we want to do is to excite a plethora of laser beams synchronized with the laser shock propagation in one dimension. So I'm not talking here about rings. So what we do is we simply use an optical cavity, a tilted cavity. So the advantage of this tilted cavity, which is a really, really simple optical device, just composed of just 2 mirrors, is that it can output a really great numbers of images of the objects that you want to use on your sample. So you can experience this yourself, as you can see on the photo on the right. Just by tilting 2 mirrors, you obtain a lot of images, a little bit spatially shifted together. And this is exactly what we need. And the temporal spread is obtained because every one of these beams, of these images, makes a round trip inside the cavity. And because the light will travel inside this cavity, at every round trip, it will experience a time delay. So this is how we obtain, from one single laser beam input, multiple laser sources spread spatially and temporally. So we have a control of the spatial temporal spread, and we can match the spatial temporal spread with the shock speed, the velocity of the shock wave traveling along the sample. So this is an experimental example here, one of the first proof of concept of this idea in one dimension. So what we do is that from our optical device, the tilted cavity, we obtain a sequence of many, many laser lines. So the first line that we excite, look at the top left image, is the line on the left. Then the second line comes next, a little bit on the right, 2 nanoseconds later, then the third 2 nanoseconds later, and so on. So when the space and the time match the shock propagation, there is pressure buildup. So on the top right, you can see like one of the experimental examples where we have been measuring the pressure of these waves along the sample surface. You can see a lot of tiny wiggles there. These are just the individual waves that goes on the wrong direction. But the most important wave is the one which is a consequence of the overlap of all these tiny waves, the big one there at 18 nanoseconds. So there you can definitely observe a huge pressure jump, transient jump, and that's a consequence of the proof of concept of this overlap of this multiple shock wave or acoustic pressure waves. So we have been quantifying this process and to understand the benefits of using one single line versus multiple lines. So we have been, the data on the bottom left figure illustrate that we obtain a gain of 25 times compared from one line to multiple lines. So we have like many times more pressure that we will have with just one laser beam. So that's kind of the proof of concept of this synchronous multiple shock pressure excitation. But to be fair, we will never reach a pressure that a megajoule laser can reach. That's totally impossible because we are using commercially available laser 1 billion times weaker. So even optimizing everything will never reach, will never be close as pressure obtained with this huge laser. So what's our idea, our main motivation? We believe that by bringing together this optical technology with the sonoluminescence, this can really make a case here. So let me explain what is the sonoluminescence. So sonoluminescence is a well-established research field dealing with cavitation, bubbles, and sound waves. So here on the left, you can see a photo taken in the laboratory of a bubble trapped in a flask. So the flask contains water, and on the flask we have glued some piezo transducer, and we have tuned the frequency of this transducer to make the flask resonate. So there, when the flask resonates, in fact it traps the bubble. So the bubble is forced to stay there at the center and to move along with the pressure field. So when the pressure grows, the bubble grows. And suddenly what happens is that at some point the bubble will collapse really violently. And this will lead to light emission, plasma formation, and this is called the sonoluminescence effect. So there have been a lot of research in this field. And right now, we have proof that the outer temperature of this little sun is in the range of 20,000 Kelvin. So it's not clear yet how much is the inner plasma temperature, because then it needs some theoretical modeling because the plasma is opaque to light, so we cannot measure inside. But it's probably from simulation 10 to 100 times higher. Another aspect here is that when the bubble collapses on itself, it releases a shockwave, spherical shockwaves that move away from the center. And from the shock speed, like you can see here, the track image on the top right, we can extract the pressure of this shockwave. And this shockwave's pressure is 40 to 60 kilobar, which is 10 to 100 times less pressure than what we can achieve with our laser shock experiments. So interestingly, the thing there is what will happen if we will reverse this shockwave, if we will drive our laser shockwave into the center of this bubble. But there are a lot of similarity between this laser shock research, sonoluminescence, and the inertial confinement fusion at NIF. So sonoluminescence as this bubble collapse entail a change of the volume about 60,000 times, which is in fact quite similar to what happens with confinement fusion experiments, where the volume of this capsule changes by 40,000 times. Because on about these plasma experiments, all what matters is how much dense, how much volume change we can drive with the experiment. This is a really key to reach thermodynamic fusion conditions. So we believe that by merging together the multi-shock focusing technique that we mastered for quite many years with the sonoluminescence effects, we could bring together, we could reach enough pressure and temperature conditions to release some neutrons from the thermonuclear fusion reaction. So one comment here, okay, Sonoluminescence can be excited with classical transducers, but laser can be used as well to induce laser sonoluminescence. So by simply focusing a laser light into a liquid, we create a bubble, and this bubble expands pretty quickly and violently collapse on itself and makes light. So these two research field, two topics, will be easily, technically, it would be doable to really merge them together. We know how to synchronize laser pulse at the femtosecond time scale. This is not difficult for us. So synchronizing everything, merging together, this is a key aspect of this fusion project here. So to summarize, our intention is to make compatible our microscale laser shock experiments with the sonoluminescence experiments. And hopefully we can reach enough pressure and temperatures of the plasma that could reach to thermonuclear fusion reactions. So right now we are on the stage of seeking government of private funding to pursue this quest. So we hope that in the next years we will be able to get our first neutrons from this reaction, and maybe like in the next 10 years, like we can design a fusion prototype, but everything will depend on how lucky we are with the next months about investments. So all the research projects that have been showing today on the research achievements have been made from a strong collaboration with smart scientists from different institutions like MIT and CNRS, and also at the international level. So if you have any question, if you are interested about this research project, if you are like us driven by this dream of building a new energy technology, don't hesitate to email myself or Keith or Steve. And now I am open for questions. Thank you very much. I hope there is enough time.
Thank you, Thomas, for your presentation. We'll be open to questions. We received some questions.
Yes, I'm listening. I'm trying to make this optical cavity here.
Okay. We were wondering if you could speak a little bit about the safety of the lasers that you're using in the sonoluminescence process.
So the lasers that we are using are commercially available. So there is not a lot of safety requirements. Of course, we have to wear safety glasses and so on, but there is no risk on that respect, and we master these conditions. We are, of course, like following the safety rules, and that's the same for sonoluminescence. The only risk there is about high voltage to power the piezoelectric transducers, but that's it. Of course, the day we will make neutrons in the laboratory, we will have to take some precautions, extra precautions in that.
Thank you for answering. We received one question on WOVA that asks, how is the system different from large-scale fusion?
Well, the key point here, the fundamental mechanisms are quite similar, but the key point is that we downscale everything, and we use really commercially available lasers, so they can fit on the table. So that's for sure. And the physics behind is rather similar. Of course, the energy level are extremely different, but the physics are known for both situations.
Thank you for your response. We got one question. You introduced fusion startup companies. Are these mostly magnetic fusions, or is it mostly laser fusion?
Almost all of them are magnetic fusion startups because it's easier to downscale the magnetic technologies and the laser technology. There is one single fusion startups that I'm aware of based on lasers.
Thank you. We have another question on startups. To what stage are the most advanced startups? Are they still in the experiment stage, scale up, or commercialization?
I mean, none of these startups are ready for commercialization. The day one of these startups can make the proof that the research have been doing can lead to fusion, they will rule the energy landscape. So, but so far, I'm not aware of a product that is kind of ready to be sold on the market.
And then in the future application, practical application of laser fusion, what are the most outstanding challenges that you see?
So this is a very interesting questions. So right now, okay, if we speak about the government's laser fusion projects, the biggest challenge there is how to improve the efficiency of the fusion experiment, because this laser is wasting a lot of energy just because we need power to supply the laser. So that's the biggest problem there. So this is how perhaps we have hope that our technology that use really moderate laser power could solve some of these problems. So we are aware that this is really high risk project, but could be a really high payoff, like any of these startups. Like the chances that this works is unknown now.
Thank you for your response. And we have another question about challenges. What has been the biggest challenges in your work personally? So far, in fact, we have overcome quite many of the problems, scientific problems that we have been facing, because we go incrementally, we go by increasing step by step the difficulties, the laser energy. So we can understand on the way, step by step, all the processes. So far, we understand how far we can go, we understand all the problems, and we even anticipate some of them, like this plateauing of the laser shock excitation. Thank you. And we have one final question. Can it create at least 1.21 gigawatts? And if so, can it be used as a power source for a flux capacitor?
I didn't get this question. Can you repeat, please?
Can it be used as a power source for a flux capacitor?
I'm not certain about that, and I don't want to say something wrong. So I will probably leave this question for later.
Okay, thank you so much, Thomas, for your presentation.
Okay, thank you very much for this opportunity. Thank you.
Thank you.